Hello, I'm Lia, one of the developers working with the virtual brain for some time now. And today I want to walk you a little bit through the technical stack and then our deployment currently done on the HBP cloud in regard with TVB Core Simulator. And let's start with some technical details of our packages. We have as a primary goal to provide easy to use simulator softwares for a large variety of users, starting from people that are able to use a command line API up to the people that want to learn a bit and use a web interface. So we built this TVB set of tools for many years now, since 2012. As Petra also mentioned, it has its first public stable version released, and it's ready to use on all the major platforms. We built it on top of Python. It is Python 3 now, with several third-party dependencies that we have a protocol to check for license compatibility as well as need in the project. We use the basic numerical libraries like NumPy, SciPy, Numba for some parallelization. For the web application, we use CherryPy plus WebGL, pure WebGL so far. We have a relational database as well. PostgreSQL is the recommended one for indexing and storing some generic metadata. As a project management flow, we use Jira, where we work currently in a Scrum manner with fixed sprints. We publish the code on GitHub. It is as public repositories available there. We use Confluence for documentation, documentation which gets extracted from the code. So we use Sphinx plus some restructured text, which is built around that. We also deploy and distribute some executable, which are ready to use, and packed with all the third-party dependencies, so the user don't need to bother with those. And we distribute the executable through our website, but also the Python modules through regular PyPy channel and Conda Forge. Plus, in some cases, we also have Docker containers, especially for the ones that require more complex installation, like the preprocessing pipeline that you just saw, where FreeSurfer and few other heavy tools are needed, including one installation where a workflow engine like Pegasus it is used. Now about the packages themselves and what are those. We have 4 packages that we name core packages. These come as Python PyPy packages, and in various combinations, they will be part of the other distributions as well. These 4 packages, 2 are more important than the others. The important ones are TVB library, which holds the simulator, and TVB framework, which holds the storage part and the web interface. Smaller packages, TVB data, as the name says, it holds some demo data for TVB, and TVB geodesic distance, it allows us for surface to compute some distances on the surface. So these packages have the dependencies like in this schema. So the framework is on top, depends on the library, which then can use the geodesic distance and the data. But TVB ecosystem is a bit larger than this. And in this, my next slide, you should see in the red rectangle, you can probably recognize the 4 packages from before. So inside what we call a TVB distribution, we put the framework and the library and the two others. And these are from maturity level, the ones that are older, and thus they have many stable releases with multiple tests and quite a good maturity. Obviously, there is always the latest version, which it goes through regular stages, alpha, beta, and then being stable again. Then around or next to these distribution core packages, we also have what you just saw in the with the reconstruction pipeline. In this drawing is in the blue box that provides input data for TVB simulator. Then in green, I have highlighted the multi-scale package, which depends on another satellite module named TVB Contrib. And this will be presented later on by Dennis as another package which is starting to become quite well tested recently. And maybe younger package, TVB Epilepsy, is one satellite module for a particular pathology. It can also be found on our GitHub repo, but is one example that the TVB ecosystem is growing. Now on the actual HBP deployment that we did for the virtual brain core distribution at CSES infrastructure. We used OpenShift for the first time, and from my feedback, it was a very smooth experience, easy to use and easy to deploy, partially because I think our package was already prepared in a container-like form. And what we did in OpenShift, in this orchestrator, we deployed two resources. One is the relational database, Postgres, as one single pod, where we store in a persistent manner the registry of the operations that we are executing inside TVB Web. And then another resource is the actual web application of TVB, which connects to the relational database. Plus, it has a persisted volume with the stored files of the data that we are using inside TVB. And this one is the one that can scale. Currently, what we set up here is based on the CPU usage. When the CPU usage reaches a certain threshold, I think it's 80%, then the number of pods automatically increases. That's a feature that OpenShift and other orchestrators are allowing. We reach up to 10 pods. That's the current configuration. But here, here currently it works smooth with the number of users that we have tested, plus a little bit of performance tests that we implemented. Here we will need to adjust based on the real usage and future real usages. Probably we will need to think of a strategy if the database, which is one single pod as a central synchronization, might be a bottleneck, so we'll need to think of that. I will talk also later a bit about this type of future work that we want to do. So that's the configuration that we did. And then you should, what you will see is this web application that Petra already showed, which opens at apps.hbp.eu. This application will allow authorization with the HBP IAM. So we created a dedicated application client in the HBP IAM where we connect and then we ask if the user has the right HBP credentials or not. And then any TVB validated, any HBP validated user will become a TVB user immediately. Now here, what we lack is some roles. We can read from the HBP key clock the roles that the current user has, but we would like to have application-specific roles. For example, Petra and myself, Misha, might want to have access to TVB settings, and then it will be nice if we could read the roles directly from the HBP key clock. Currently, we have a workaround this, but maybe we can discuss how it could be solved in a more standard manner. And from there, after login, one gets access to this a beautiful web application where one can learn about the virtual brain flow. And one important aspect I want to emphasize about our modeling. Inside the virtual brain framework, we work with an important entity which is called project. This project, it is a flexible grouping entity that we leave at the hand of the user to decide what granularity it has and what will he or she put inside. So a project is a container from our perspective of operations and their results, which are under the form of data types. And one user can share this unit of grouping then with other users, which are called members of that project. We envision this as a lab who is having a study case, and then it shares that study case with all the members in that lab. But it's up to the user if this project contains one single subject, or it contains a group of subjects which all participate in the same experiment, or it holds only one recording for one subject, because that's the sharing unit that he or she decides to use. So we really like this entity. It proved over years to be a good and flexible unit of sharing, as sharing happens on it. Within TVB, we evolved towards an architecture which is data-oriented, meaning that our data are organized in a graph, like the structural connectivity, the cortical surface, time series, and so forth. All these, they are classes in the software code, and on the drive, they are files. So we have one H5, HDF5 file for the structural connectivity, one file for the cortical surface, one for the time series, and so forth. And this file should be self-contained regarding the proper data of that entity, but they also contain references. For example, time series region will be generated on top of a structural connectivity, so it will refer to the global unique ID of that structural connectivity. So this is at the center, the data that we organize in classes and then goes on the files. Around this, we organized our operations, which can be of multiple types. One type of operation, very important, the main one for TVB, is the simulator. And such an operation takes as input some data types, 0 or multiple, and produces 0 or multiple results, other data types that are again persisted and possibly used as inputs in other operations, like the result of a simulation will be a time series, which will be used in an analysis, could be used in an analysis later on. So this is our data-oriented architecture which we developed within TVB, and this allows us to have some distribution already. And I want to emphasize the distribution part in the next sequence schema, because with the data available, then one can think of operations distributing on multiple environment or multiple machines to be executed in the cloud. And here is our current use case. And I will briefly go to this sequence schema. We have 3 columns. The business logic is in the first one with the framework, and then the storage happens in the last 2 columns with the relational database and the file storage. So from the framework, we can submit an operation as a configuration which goes in the storage. And then we only schedule a launch, even if it happens that TVB is deployed locally on a laptop, we still do just the scheduling of launching the simulation. And then the scheduler, in this case a queue, if it's a local, it could be a Slurm or whatever, if it is a cluster, will come to execute the operation, which is given by some unique ID, which is very simple. Then it will go to the storage in order to read the configuration and the inputs. It will execute the operation, and then it will write back the results and notify that the state has finished. So here, the actual flow with the TVB framework as 1 column. It is for the local installation, but we can imagine that different instances can exist, and then it will go in a cloud. And we will see later on a more complex schema where that happens. So for HBP, in the dev environment, we have in work and already with good progress, the capability to push these jobs towards the HPC backend. It's Daint in this case. So we have the blue box on the left, which is the web application that you already saw, with OpenShift, with a Docker container, which is then executed, a local storage and the local index DB, plus the HBP IAM accounts, which can log in. Then at the point of scheduling an operation, we developed for this particular deployment, but okay, for this use case, but in a generic manner so that other HPCs could be used as well, we added a step which is called stage in, where we encrypt the data needed for a particular operation, then we copy it on the HPC, we schedule with PyUnicore the execution of an operation, which when will it run in the backend, will have its own Docker image with the same software, TVB software installed, plus it will do some supplementary steps now of decrypting the data, first requesting the password, then decrypting the data in memory, running the simulation, and then communicating back with the web frontend that the result is done. And then the web interface, it does a staging out through PyUnicore again, copying back the encrypted results into the central web application to be available for inspection by the user. And what I just explained to you, it is drawn here as a sequence diagram. It's not important that you read all of the errors, but just please bear with me while going through the headers. So we have now, again, the TVB frontend, which is the web application, plus the services. This will be the logical blue box, the OpenShift deployment, with the storage, the database, and the file storage. And now we have a new column here on the most right side, which is the HPC TVB. And the errors will be the same as in the previous sequence schema. We serialize, put the data in the storage, but we have an additional step when launching the when scheduling the operation to do a stage in, and then a stage out when the operation is done, plus the regular updates on the front-end OpenShift deployment. In the next slide, I have briefly described the messages that are passing with the HPC backend through PyUnicore API or Unicore, where we start a job on the HPC, we monitor it, we might receive a job complete status, and then we request the files and send back the results. So just more details about the staging, stage out. Here we have an important rule that we keep and use the files encrypted as long as possible. Only when the job starts, they will be decrypted. The key for decryption is not kept together with the data. One would need an authentication within HBP keyclock again from the HPC job in order to request, this time to a REST API, the password to decrypt, and then it will decrypt, encrypt, and send back the notification that the job is done. So this part, it is as a proof of concept in terms of maturity, currently now on HBP OpenShift development environment available. Any questions so far? Okay, I assume not. I have then just one more slide about the next step or what is still work in progress. As a summary, currently we are working on TVB version 2.1, which means the current version is still having some not finished features. We have as an important new feature a new API through REST. We are using it successfully within the Virtual Brain Cloud when developing a new graphical interface, this new REST API. We start to go towards something like microservices, and I put this in quotes because I think we are far from being a microservice-based architecture, but we are separating and improving our modularization as long with any new case that we have of deployment and usage. One such example in the Virtual Brain Cloud is the development of a separate data registry and repository that will be used as a service by the TVB core. So then we won't have the local DB and the local file storage, but we will connect to a registry and repository service. You will hear more about multiscale, and within eBrains, the integration that we are working right now, it is on improved security. I briefly mentioned you about the encryption, decryption that we do. There we still have a little bit of work until we can put it in the production, but I think we are on a good stage. You will hear later about domain-specific language accelerators, GPU, and so forth, and the Atlas integration as another work in progress, hopefully to happen soon, next step. And with this, I conclude my presentation and leave you with two URLs. The first one is the technical documentation of the virtual brain, docs.thevirtualbrain.org. The second one is the virtualbrain.apps.hbp.eu, the production OpenShift deployment of the virtual brain web within HBP.